Hello and welcome to all students. In this lecture we learn about the first order first degree differential equations. This is calculus first and unit number 3, BSc part 1, first order and first degree differential equation. So in this lecture, first of all, we see the definition of a differential equation. Then we define order of a differential equation, degree of a differential equation. Then ordinary differential equation. Then we define what is meant by partial differential equation, linear and non-linear ordinary differential equation, and solution of homogeneous and non-homogeneous differential equations of first order and first degree, and notation of partial differential equation. And in the next lecture we learn about some exact differential equations. Okay, so let us start the definition of our differential equation. So first of all, we see some examples of differential equation. So in physics, engineering, and chemistry, and increasingly in such a subject as biology, uh, sociology, and economics, it is necessary to build a mathematical model to represent certain problems. It is often the case that the mathematical model involves the search for an unknown function that satisfies an equation in which derivatives of an unknown functions play an important role. Okay, such equations are called as differential equations. Means the equations which contains derivative of some unknown function, derivative of a function, that equation is called as a differential equation. As in equation 3 below, a derivative may be involved implicitly through the presence of differentials, or aim is to find method for solving differential equations, that is to find the unknown function or functions that satisfy the differential equation. The following are examples of differential equations. So here first example is dy by dx is equal to cos x. This is the example of differential equation. Second is d2y by dx square plus k square into y equal to 0. This is another example of differential equation. One more example, third example is x square plus y square into bracket into dx minus 2xy dy equal to 0. Third example. Now fourth example is dou u by dou t is equal to h square into bracket dou 2u by dou x square plus dou 2u by dou y square bracket complete. So this fourth example of differential equation is called as partial differential equation. It's called as partial differential equation because it involves a partial derivative of some function. Okay, so let us look towards the fifth differential equation, L into d2y by dt square plus r into di by dt plus 1 upon c into I equal to e into omega plus cos omega t. So this fifth example of a differential equation is a application of differential equation in electric circuit. So let us go to the sixth example of differential equation, dou 2v by dou x square plus dou 2v by dou y square equal to 0. This is also a application of differential equation. Okay, partial differential equation. So see here, lots of examples of differential equations are given here. You can see when an equation involve one or more derivatives with respect to a particular variable, that variable is called an independent variable. Okay, see once again, when an equation involves one or more derivatives with respect to a particular variable. That variable is called as independent variable. In the example 11, x is a independent variable, y is also independent variable, and f is a variable which is dependent variable, and it depends on x and y. Okay, variable is called as dependent if a derivative of that variable occurs. Okay, so in the example of 11th example of this differential equation, the derivative of variable f occurs, therefore f is called as dependent variable. F is called as a dependent variable. In the equation, L into d2I by dt square plus R into di by dt plus 1 upon c into I equal to E into omega cos omega t. Here I is a dependent variable because its derivative occurs, and t is the independent variable, and L, R, C, E and omega are called as parameters. Okay, so let us go to the next differential equation. D2v by dx square plus d2v by dy square equal to 0 has a one dependent variable, and that variable is v because its derivative occurs, and two independent variables and these two independent variables are x and y. So in the equation x square plus y square dx minus 2xy dy equal to 0 may be written as x square plus y square minus 2xy into dy by dx equal to 0. So in this differential equation, y is okay, we may consider the either variable to be we may consider or the same equation we can write in the other format, x square plus y square into dx by dy minus 2xy equal to 0. We may consider either variable to be dependent, the other being a independent variable. So in this example, so sometimes we consider y. So if we write our differential equation in this format, x square plus y square into dx by dy minus 2xy equal to 0, in this format we see here x is a dependent variable and y is independent variable. But if we write our differential equation in this format, x square plus y square minus 2xy into dy by dx equal to 0, so from this differential equation we can say that y is a dependent variable and x is independent variable. So in this case we can change the dependent variable and independent variable by writing the differential equation in different format. Okay. So we have some exercise. So this is exercise. This exercise is for students. Identify the independent variables the dependent variables and the parameters in the equations given as an example in this section. Okay, so let us go to the next now, the definition of a order of a differential equation. Okay, the order of a differential equation is the order of the highest ordered derivative appearing in the equation. Okay, so this is the very simple definition of a order of a differential equation. So in the other word, the order of a differential equation is nothing but the order of highest order derivative appearing in that differential equation. This is the order of that differential equation. So see, one example is given, d2y by dx square plus 2b into dy by dx cube plus y equal to 0. So in this differential equation, the highest order of a differential derivative is 2, because here the derivative with highest order 2 is appearing in this differential equation. Okay, so therefore the order of that differential equation is 2. In this equation, the order in okay is the differential equation, and the order of that differential equation is 2. It is also referred to as a second order equation. second order equation. More generally, the equation More generally, the differential equation may we represent like this: uh, f of x comma y dash comma dot comma yn equal to 0. Means left hand side is a function of derivatives and independent variable. Derivatives are function, its derivatives and independent variable. Okay, so the order of the differential equation is 2. So general form of a differential equation is given here: f of x comma y dash comma comma yn equal to 0 is called an nth order ordinary differential equation. Under the suitable restrictions on the function f, equation 2 can be solved explicitly for yn in terms of the order in terms of the other n plus 1 variables x y dash comma yn minus 1. To obtain yn, we can write the differential equation yn means nth derivative of y. It is equal to f of x y dash comma y n minus 1, and this is third equation. For the purpose of this, we shall assume that this is always possible. Otherwise, an equation of the form 2 may actually represent more than one equation of the form of equation 3. For example, the equation x into y dash square plus x into y dash square plus 4y dash minus 6x square is equal to 0 actually represent the two different equations, and these two equations are given here because y dash square above equation is a quadratic equation and it is quadratic in quadratic in y dash. Therefore we can solve that quadratic equation and we get two roots, and these two roots are nothing but two differential equations. We can solve these two differential equations separately. A function phi defined on an interval x greater than a less than b is called a solution of the differential equation 3, provided that the n derivatives of the function exist. Okay, on the interval x greater than a less than b, phi n x, for every x phi n x is given here, and for every x is greater than 0 less than b. For example, let us verify that y equal to e raised to the power 2x is a solution of the equation d2y by dx square plus dy by dx minus 6y equal to 0. So simply the function is given here y equal to e raised to the power 2x. We take its second derivative, we take its first derivative, and just put in the left hand side of the equation 4, and we see that the left hand side becomes 0, which complete the desired verification. All the equations we shall so all the differential equations of first order and first degree, they may be written in the form of dy by dx is equal to f of x comma y. So this is the general form of first order and first degree differential equation. For such an equation, it is sometimes convenient to use the definition of elementary calculus to write the equation in the form of m dx plus n dy equal to 0. And a very important concept in the study of differential equation is that the linearity. An ordinary differential equation of order n is called a linear if an ordinary differential equation of order n is called linear if it may be written in the form of b naught x dny by dx raised to n plus b1x plus dn minus 1y by dx raised to the power n minus 1 plus bn minus 1x dy by dx plus bn x y equal to rx. For example, the equation 1 above is linear and equation 4 is linear is linear. The equation x square into y double dash plus x into y dash plus x square minus n square y is equal to 4x square is also a linear differential equation. Okay, so now let us we stop here, and we will continue our next lecture. uh, okay, so remaining part we will continue in the next lecture. So let us we stop here. Thank you very much.